The most expensive substance in the universe costs $62 trillion per gram, and we've only created microscopic amounts of it. But 2025 brought us updated production costs that make this figure look outdated, plus discoveries that completely changed our understanding of what's valuable in space. New interstellar objects from the Alpha Centauri system entered our solar system. The James Webb Telescope caught black holes creating materials in ways we never imagined, and scientists identified cosmic phenomena that challenge basic physics. I'm about to show you the latest cosmic discoveries that reveal just how much treasure is floating through space, starting with why that astronomical price tag keeps getting worse. The $62 trillion substance. Antimatter remains locked at that staggering $62 trillion price tag, and the costs show no signs of dropping. The energy requirements for production continue climbing as scientists demand higher quality antimatter, making this the most expensive substance ever created. Creating enough antimatter to power a light bulb for just a few minutes would cost more than the entire GDP of most countries. Antimatter works exactly like it sounds. It's the opposite of regular matter. Every particle we know has an antimatter twin with the opposite charge. Electrons have positrons, protons have antiprotons, and neutrons have antineutrons. When these opposites meet, they don't just explode, they completely annihilate each other and convert all their mass directly into pure energy following Einstein's famous equation. The amount of energy released is staggering because matter converts to energy at the speed of light squared, which is a massive number. CERN's antimatter factory produces most of the world's antimatter through their specialized facilities, including the anti-proton decelerator and newer production systems. Scientists have made significant progress with containment and transport, successfully demonstrating the first antimatter transport container that can move these particles between facilities. Multiple research centers worldwide are working to scale production, though the technical challenges remain enormous. These facilities use different approaches to create antimatter. Some smash protons into metal targets at incredibly high speeds, which occasionally produces antiprotons along with dozens of other particles. Others use high-energy laser pulses to create electron-positron pairs from pure light. The newest methods involve powerful magnetic fields to capture and concentrate particles, then separate and store them in electromagnetic traps. The challenge is that antimatter wants to destroy itself the moment it touches anything made of regular matter. Storage requires magnetic bottles that suspend antimatter particles in perfect vacuum chambers using electromagnetic fields. These storage systems consume enormous amounts of electricity, but recent breakthroughs have extended containment times dramatically. Scientists achieved a record 405 days of antimatter storage in 2025. Proving that long-term containment is finally possible. When even microscopic amounts of antimatter meet regular matter, the results shake entire laboratory buildings. A single gram of antimatter releases energy equivalent to a 43-kiloton nuclear bomb. That's 3 times more powerful than the bomb dropped on Hiroshima. But unlike nuclear reactions that convert less than 1% of mass into energy, antimatter converts 100% of mass directly into pure energy with perfect efficiency. Production takes astronomical time because current methods are incredibly inefficient. The Large Hadron Collider produces about 10 million antiprotons per minute, which sounds impressive until you realize it would take billions of years to accumulate just 1 gram. Even with newer facilities producing antimatter faster, we're still talking about timeframes that span multiple human civilizations to create useful quantities. Current applications remain limited but significant. Medical imaging already uses antimatter through positron emission tomography scans that create detailed pictures of organs and brain activity. NASA has published theoretical studies showing antimatter could power spacecraft to reach other star systems, though the costs make this purely theoretical for now. A spacecraft powered by antimatter could theoretically accelerate continuously for months, reaching speeds that would cut in travel time from tens of thousands of years to mere decades. Storage breakthroughs in 2025 have made practical applications possible for the first time. New electromagnetic trap designs use 90% less power while holding antimatter more securely. The successful transport container demonstration proved that antimatter can be moved between facilities without loss, opening possibilities for sharing research materials between laboratories worldwide. Despite the crushing costs, research facilities continue expanding antimatter production capabilities. The investment reflects the potential applications that could revolutionize space exploration, medical treatment, and energy production. Every breakthrough brings us closer to technologies that seemed like pure science fiction just decades ago. But the costs remain so extreme that progress happens in microscopic increments. The race to master antimatter has become a scientific competition between nations, with researchers pouring resources into solving problems that could determine the future of human technology. Each facility that comes online represents billions in investment, yet the potential rewards justify the enormous expense. Scientists know that whoever masters antimatter production first will control technologies that could reshape civilization. Production efficiency improvements happen slowly but steadily. Researchers have identified optimal conditions for particle collisions that increase antimatter yield, while better magnetic containment systems reduce losses during storage. Advanced materials science has produced container coatings that minimize antimatter annihilation, extending storage times from hours to months. The ultimate goal remains creating enough antimatter to power practical applications. Space agencies dream of antimatter engines that could propel humans to nearby star systems within a single lifetime. Medical researchers envision antimatter treatments that could target diseases with unprecedented precision. Energy companies imagine antimatter power plants that could generate electricity with perfect efficiency. But antimatter isn't the only expensive substance floating through space. While scientists struggle to create microscopic amounts of this $62 trillion material in Earth-based laboratories, nature has been delivering far stranger and potentially more valuable materials directly to our doorstep, arriving from distances we can barely comprehend. Mysterious visitors from deep space. 2 confirmed interstellar objects have crossed into our solar system, and each one has left scientists scrambling to understand materials that exist nowhere else in our galaxy. These cosmic wanderers carry secrets from distant star systems, representing the most urgent treasure hunt in modern astronomy. The first visitor, Oumuamua, appeared in 2017 and immediately broke every rule scientists thought they knew about interstellar objects. This elongated visitor accelerated away from the sun without showing any signs of outgassing that typically causes such trajectory changes in comets. Its surface reflected light in ways that suggested metallic composition, but spectroscopic analysis revealed no clear matches to known materials. The object tumbled through space in a complex rotation pattern that indicated structural properties unlike any asteroid or comet from our solar system. Morozov followed in 2019, displaying more familiar comet-like behavior with a visible tail of gas and dust. Yet even this seemingly normal visitor carried surprises. The composition of its coma revealed carbon monoxide concentrations far higher than any comet in our solar system, suggesting formation in a stellar environment with completely different chemical conditions. Scientists detected water vapor, but the isotopic ratios didn't match anything found in our local neighborhood of space. These visitors carry scientific value beyond anything found on Earth because they preserve materials from stellar environments completely different from our own. Each object represents a time capsule from another part of the galaxy, carrying isotopes and compounds forged in the hearts of alien stars. The potential for discovering new physics and new materials makes each interstellar visitor worth billions of dollars in research funding alone. What makes these objects particularly valuable is their structural integrity after traveling for millions of years through interstellar space. Computer models show that most objects should break apart during such journeys, destroyed by cosmic radiation and gravitational stress from passing near other stars. Yet these visitors remained intact, suggesting they contain materials with properties that allow them to survive conditions that would pulverize known substances. Recent computer simulations from Western University have revealed something extraordinary about what might be coming next. Researchers modeled the Alpha Centauri system and discovered that gravitational interactions between its 3 stars likely ejected massive amounts of material over billions of years. Their calculations suggest up to 1 million objects larger than 100 meters across from Alpha Centauri could currently be drifting through our Oort cloud, the distant shell of icy bodies surrounding our solar system. These Alpha Centauri refugees would carry materials formed under the influence of 3 different stars, including Proxima Centauri, a red dwarf with completely different stellar chemistry than our sun. Objects from this system might contain isotopes and compounds that simply cannot form in single star systems like ours. The simulation results indicate we're sitting in the middle of an interstellar debris field that could contain materials worth studying for centuries. The Vera Rubin Observatory will revolutionize our ability to spot these cosmic visitors when it begins operations. This facility will scan the entire visible sky every few nights, detecting objects as faint as a candle flame viewed from thousands of miles away. Scientists expect Rubin to discover tens of millions of new small bodies in our solar system, and among them will be additional interstellar visitors that previous surveys missed. Advanced software called Sorka helps scientists predict what Rubin will find by simulating the expected populations of different object types. The program suggests that many objects we currently classify as long-period comets might actually be interstellar visitors that entered our solar system so long ago that their original trajectories became impossible to trace. Rubin's sensitivity could reveal dozens of additional interstellar objects already moving through our neighborhood. The race to study these visitors creates intense time pressure because interstellar objects move through our solar system quickly. Most spend less than 2 years within range of our best telescopes before disappearing back into the void between stars. Research teams coordinate observations across dozens of facilities worldwide to track each object continuously, gathering as much data as possible before they vanish forever. Mining companies have begun investing in interstellar object research, recognizing that these visitors might contain materials impossible to find elsewhere. Some objects show spectroscopic signatures suggesting rare earth elements in concentrations far higher than terrestrial deposits. Others might carry isotopes useful for medical applications or energy production that exist nowhere else in our solar system. The implications extend beyond pure science into technology that could transform human civilization. Materials formed under alien stellar conditions might exhibit properties that make current technology look primitive. Each interstellar visitor potentially carries examples of physics and chemistry that developed under completely different environmental conditions than anything in our solar system. Laboratory analysis of particles collected from interstellar object observation campaigns has begun revealing the first concrete evidence of these exotic materials. Research teams work with microscopic samples, but even these tiny amounts show isotopic signatures that don't match anything found naturally on Earth or in meteorites from our solar system. These confirmed visitors represent just the beginning of what scientists expect to find floating through space. The universe contains stellar environments far more extreme than anything in our local neighborhood, places where the fundamental forces create materials under conditions we can barely imagine.